Hi, in today's video we're going to be talking about carbocation rearrangements. And so this was alluded to in a previous video when I said things can go awry when you form carbocations. So if we look at how carbocations are stable, we often invoke hyperconjugation, where we have this carbon-hydrogen or carbon-carbon bond adjacent to this carbocation, and it's donating a little bit of electron density. So again, if we think about a secondary carbocation, now if we look at a system where we have a secondary carbocation, and adjacent to it we have a carbon with other carbon atoms, there can be a scenario where these electrons are being shared a little too much, and then all of a sudden we've actually formed a new carbon-hydrogen bond and generated a different carbocation. In this case, this is a tertiary carbocation, and it's more stable. So this is a more favorable process. We call this a 1-2 shift, and the numbering system comes from the fact that one atom, in this case a hydrogen atom, has moved over two atoms. So again, this one atom has moved over a two-atom system, so that's where you get this 1-2 shift. And again, it's similar to hyperconjugation, but imagine the hyperconjugation has gone a little bit too far, and now it's formed a new bond. And again, the reason why this is favorable is that you've gone from a secondary carbocation to a more stable tertiary carbocation. I'll point out that this CH bond is still helping the stability of this carbocation. It is still donating electron density into the carbocation, but now it's just doing it from a different atom's perspective. So let's look at some mechanisms associated with this and see some examples of when this can occur. So if you have this type of alcohol and you treat this alcohol in the presence of a strong acid, it's going to get protonated. And when it gets protonated, it can form a secondary carbocation. So now you have a scenario where you have a secondary carbocation directly adjacent to another position where another carbocation could form. I've highlighted that bond in purple here. So the arrow pushing looks like this, where you have the electrons from this carbon-hydrogen bond now going over and forming now a bond to this, or forming a bond with this carbon. So now again, you're going from where the electrons are to where they aren't. Notice that this arrow does not go between these two bonds. That would form a double bond, and that's how we show our elimination mechanisms. So we've gone from a secondary carbocation to a tertiary carbocation. That's now favorable. And I also like to keep track of the fact that we had hydrogen atoms on here all along. This carbocation can now undergo SN1 chemistry or E1 chemistry to give you this substituted alkene or this tertiary alcohol. I'll point out that this secondary carbocation could also undergo the same E1 reaction. So when you form this product, you actually don't know if this 1-2 rearrangement occurred or not. I'll point out that on quizzes and exams, I'll often ask you, how did this kind of thing form? You don't have to make the assumption that something formed until I give you a product where it seems a little off that it occurred. Also, I'll point out that this secondary carbocation can also undergo SN1 chemistry. And so you could also have the alcohols originating from that. So in the case where there's 1-2 shifts in action, lots of different products are possible. Let's look now at this alcohol where instead of having a hydrogen and two carbons, we have 3 carbon atoms. So again, this alcohol is going to protonate and it can form a secondary carbocation. Now, unlike the previous example, we didn't have a carbon-hydrogen bond, we have carbon-carbon bonds, but those can also undergo 1-2 shifts. And so in this case, the whole carbon with its 3 hydrogen atoms, this whole methyl group, shifted over 1 to form now the more stable tertiary carbocation as compared to the secondary carbocation. This tertiary carbocation can undergo SN1 chemistry. It can also undergo E1 chemistry to form this highly substituted alkene. I'll point out that this particular compound is going to give you a different E1 reaction product, in this case because there's the only protons available to it to remove in the context of E1 chemistry exist at the terminal carbon here. Thank you for your time, and I look forward to answering your questions about this complicated or challenging reaction. I will point out that, again, this is one of the reasons why we as organic chemists often try to avoid forming carbocations of this type of this sort in reaction mechanisms, because all sorts of things can really occur. All right, thank you for your time.